Just going to take attendance. I'm still not good on names. Isabel. Thank you. Sam, Dyke. Finn. Callum. Jamie and Sam. Brooke. Ronan's not here. Anna. And William. Marcus, I already ticked you off. I don't know why I missed you. And Hunter's not here. I haven't met Hunter yet. But he might listen to this recording, so hi, Hunter. Cool. Okay, so that's probably enough time for you to go. How did you go? What did you think about the first one? PS, dots, or N? Isabel, what do you reckon? Yep. That's pretty straightforward, I think, isn't it? It's got two terms. They're subtracted, but it's just a square there. So that's all good. 3x plus 7 times 7 plus 3x. PS, dots, or N? Sam? It's not dots, because for dots, you'd need for one of them to be subtracted from the other one, yeah? So it's not dots. So here, it is true you can reorder them, but because both of these terms are positive, if I reorder them, they'll be positive as well. So if I reorder them, I could put 3x here and 7, but kind of like the sign goes with them, so that's still positive, and 7 is a positive number, and so we say it's still positive there. So you're right that you can reorder them, but the reordering doesn't give us a minus, if that kind of makes sense. Yeah, cool. So it's 3x plus 7 times 3x plus 7 if we order them. And what does that mean, Anna? Perfect square. Does that make sense? So I've deliberately put gotchas in there, right? So don't, that's what they're there for. X squared plus 2x minus 2. Which of those is it? Sam? Other Sam? Sorry, Mule.
Is that neither?
It's a neither. Yep, or neither neither. Yep. I wasn't correcting you then. Yeah. So although it looks like they're almost the same, there is a precision in mathematics that you need to be very careful. That's what you need to train your brain with, precision. So I put my gotcha there, of course, is that it kind of looks like a something plus something and a something minus something, and they kind of look the same. But because of that square on the first term, this one here, that's not there on the first term of the second bracket, they are not samey enough to say that they are a difference of two squares. So if you put dots, make sure that you get why it's not dots. Okay, what about this one? Q plus R plus T all squared. Marcus, what did you put? Perfect square. We agree? It is, isn't it? But it's not a straightforward perfect square in that some manipulation happens. Now, I didn't show you this last time, but for example, you could do this if this helps make more sense of stuff. What makes it not fit the pattern in a way is that there are 3 terms instead of 2. We can see that, I hope. One thing you could do, and again, do this bit in your head rather than necessarily writing it out like I am. You could go, let big A equal Q plus R. Then we have A plus T all squared. See how I just replaced the Q plus R with the A? Which we now can see is a perfect square, I hope, which we then substitute back in and I won't do the last line, but then you can expand Q plus R all squared as well. So it's a perfect square within a perfect square. But you keep on expanding stuff out and collecting like terms if you have to, blah, 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 blah. So that's a little trick that sometimes with algebra, if the algebra is getting a bit too much, use a substitution step like that to get rid of something which is common, and it simplifies what you're trying to do at the time. And therefore, you're able to sort of concentrate on one bit of the problem at the time rather than trying to juggle a Q plus R as well as a T. If you don't need to do that because you're kind of good with it, that's fine as well. It's just a suggestion if that would help your mathematical thinking. Okay, number 5. What is it? Jamie, what did you put? Dots, but it might not be right. Okay, Jamie's speaking with an air of confidence there that he doesn't have. What do other people write? You think it might be what? But now you think it might be neither? Okay. What about other people? Let's just do a quick straw poll. Who put neither? Who put dots? Who put perfect square? There are some people in this room that didn't put any hand up there. Now that makes me think that either you had no idea at all and so you just left it blank instead of taking a stab, or you put down I am a fish or something like that as your response. Right, okay. So just so you know, if you're a little bit, I won't get you to do this in case people have got chewing gum, but if you check the underneath of your chair, you'll find there is no electric buzzer there. So if you do get something wrong, you won't get an electric shock. So always take a stab, please. Remember, that's the key to success, thinking it through, taking a stab, working out sometimes why you got it wrong, okay? We are allowed to use the F word in this classroom, not the one you're thinking about. You're allowed to say, I failed to get that right. That's the F word you're allowed to use. Okay, let's have a look at it. It's first things first, it is definitely not in the right format for dots in that it's 3x minus 7 and then it's minus 3x plus 7. So it's not in the right format yet, but it's worth just manipulating to see if we can do anything about it. So I'll leave the 3x. Whenever I see negatives, it's something to do with the negatives that's worth manipulating, and maybe we won't get anywhere. So if I could reorder them so we do have a subtraction. Just trying to erase that. So I could go 7 minus 3x instead. See how I've just changed the order of the terms. But that's no good for difference of 2 squares because they're now both subtractions. Plus, it's no good for perfect square because they have to be in the right order with a subtraction because 3x minus 7 is definitely not the same number as 7 minus 3x. Substitute in 1 for x and you'll get that. So that's not right. That doesn't work. The other thing that's worth trying in your manipulations is to take a negative outside the bracket and see what that does. So can you see how I put the multiplication back in there just while I'm doing this, just to make it easier? So if I take a negative 1 outside the bracket, I would be left with positive 3x minus 7. That's good news. Because, again, just to clarify, minus 1 times 3x is minus 3x. Minus 1 times minus 7 is plus 7. So that's all I've done. I've taken a negative 1 out. And it's good news because who can see it? Perfect square, apart from that negative 1 floating about. So basically, I can say that's equal to negative 3x minus 7 times 3x minus 7, which is now a perfect square. Does that make sense? Again, if you could just look at that and go, oh yeah, that's a perfect square, that's pretty obvious, then there's no point you being in Maths Methods Foundation, right? We've got 2 415s here from last year that didn't tell me straight up that it was a perfect square. So this is not about, oh, if you didn't get it, you're stupid. It's about, this is the kind of thing you need to train yourself. The more you look at, the more you force yourself to look and experiment, the more likely it is you're going to be able to uncover these patterns. A plus B minus C, A minus B plus C. Is that perfect square? Or is it dots? Or is it neither? William? Neither or dots? What makes you suspect that it might be dots? It's worth exploring, isn't it? It's worth exploring. It might be dots. It might even be perfect square, but I don't think it would be. I think my money would be on dots as well, or neither, one of those two. So a quick check. Again, this is the sort of thing that over time you just get more used to. So it's that manipulation of negatives to see what we can give us. So I can see that I've got an A plus B minus C, and I've got an A minus B plus C. So what I'm really asking myself is, can this bit here be manipulated to look like this? Or it could be the A plus B is grouped together, but that to me looks a little bit more tricksy because I can't take a negative outside because it would make B positive and A negative. So I can't really see that changing to an A plus B, but a negative on this side does look suspiciously like as if it might give us something. So if I just put brackets around the B minus C like so, and take the negative out, let's see what's left inside the brackets here. I'd be left with a B, and because it's a positive C here, I will need a minus C inside the bracket because so that the two negatives make the positive. So your instincts were right. It does give us A plus something, B minus C, multiplied by A minus something, B minus C. Boom, boom. So then we can use dots. In fact, if I was being a bit more precise, I'd probably say, I didn't have this as an option, it's actually both. Because it's dots to start with, square the first, square the second, square the first minus square the second. But then to finish the expansion, I'm going to have to use perfect square on B minus C. Okay, so it's actually twice. It's actually both there, but I wasn't looking for both. I was really just looking for dots. And the last one. Finn, what do you have for the last one? Yeah. It is, so therefore? Yeah, perfect square or neither? Yeah, neither or perfect square. I would argue. In that you could say it's a perfect square. How could you make that a perfect? I've run out of room here, but how could you make it a perfect square problem? I heard some good mutterings there that seem to say the same thing. I'm just going to squish this in a little bit. Sorry, because I just run out of room a little bit. You could make this x plus 1 times x plus 1 all squared. And then you could say that's x plus 1 times x squared plus 2x plus 1. And then you could do another expansion. So technically you could at least make your life a little bit easier by doing that. Does that make sense so far? Okay, so as I sort of warned you last lesson, we're going to try and do something new for most lessons. And the anticipation is that you're doing work outside of class to ensure that you're keeping up with the material. And if I don't hear from you, then that's because you're okay with it. And please don't hesitate to reach out to me. I'm in the math study a lot of the time, and if I'm not, I'm always connected to my email. So if you say, can we make some time to go through difference of two squares? I didn't quite get question 7. I'm happy to do that. Also, because of this technology sort of thing here, if you specifically say, hi Richard, I'm at home and I'm trying to do question 7B and I can't get it, can you give me some hints? I can quickly put a video together and then just send you the video via an email so you can sort of get some help on the spot. So don't hesitate to use those avenues of support, please, because I don't want to make assumptions about you being ready when you're not. I'm just I'm dependent on you communicating how much you can do. So, including if I'm going too fast or too slow. So far, we've looked at challenging examples of difference of two squares and perfect square. That set of 7 problems I just gave you, feel free to do them at some stage. But we haven't covered any new material yet. So we're about to start looking at that. If you've done Maths Extended last year, obviously 4 and 5, then there's not going to be masses that are new at all over the whole year. And that's okay. It's worth revisiting anyway, because otherwise you wouldn't be here if you didn't feel like you needed to revisit it. If you didn't do maths extended, the next bit's going to be a bit new to you. So see how you go. So what I want us to do is I want you to use whatever method you want to. I want you to expand x plus 1 cubed, please. So expand and simplify. Is my writing okay down the back? That's not too small? Just a point on language more than anything else. When you don't put brackets around that, it's like you're saying it's x plus 1 times that. So you have to have those brackets. Yeah, looks good. So what's that number?
3.
Come on, man. What's 1 cubed?
1.
Hello.
I put 1 there, so James. Everyone should be getting that.
I didn't even look.
It's supposed to be 1, mate.
Come on, brother. What's 1 cubed?
I changed it because I copied.
Yeah, keep going. Oh. What's that number?
2. Oh, what?
What's 1 squared? What have you written?
1 times 2.
What I've worked out is at least 50% of the class don't know their 1 times table.
I thought it was squares.
Okay, cool. Yeah, good step. Missing a bit. So you've got x times x cubed is x cubed, x times 2x is 2x squared, x times 1 is x. Great. Now do 1 times each of those and put them on the end. And then you're nearly done. Same with you. X squared plus 2x plus 1, so that's right. So plus x, and then 1 times x squared is x squared, 1 times 2x is blah, blah, blah. Still doesn't look quite right to me. Simplify, collect like terms. So you've got a 2x and an x. You've got a 2x squared and an x squared. Simplify. Oh, I was going to say it's a good start, but it's the problem I just gave you. Great.
I'm not entirely sure. So I'm just
No, good. That's fine. So there's 2 things you can do. You can either see that that's a square, perfect square, and expand that first. But really, you can't do, if you do have 3 expressions, one after another, you can't do all 3 at once. So you just chunk it down a bit. So you do that expansion first, and then you'll get a bracket with 3 terms, and then multiply it by the, yeah. It was really gratifying to see a number of people starting off with that. That was really good. So recognizing that you could split the cube into 1 of it and then 2 of it in powers. So that's really nice. And then applying the pattern to the right-hand side here, so that we've got x squared plus 2x plus 1, not 2. 1 times 1 is 1. And then you can chicken beak the rest, or box method it, or just do it. And again, I'll just remind you of the little, I think, a really useful way of setting out this problem and by putting like terms underneath each other. So first of all, I'm going to multiply x by x squared, x by 2x, x by 1, and I get x cubed plus 2x squared plus x. Then I shift over 1 to write my next line down, because I'm going to be doing 1 times x squared, which will give me an x squared term, 1 times 2x, 1 times 1. So over here, I'll shift over and I'll just do that. 1 times x squared is x squared, 1 times 2x is 2x, and 1 times 1 is 1. And then I can sort of do a column add, x cubed plus 3x squared plus 3x plus 1. So now we have an expansion for x plus 1 all cubed. There's method to my madness, right? I'm going somewhere with this, so don't think I'm just punishing you. What about x plus, oops, try not to do that one, x plus 1 to the power of 4? I can think of 2 ways that could be done. Shorthand. I might not give you enough time to do this next one. As in, don't stress if I move on and you haven't done it, but having an approach to doing it is a valuable thing, which is what I'm just going to check on. How are you going to tackle this? Yep, that's one way, definitely. Two squares, yep. What are you going to do? No, do it. See, if you can work out the pattern, use that pattern. Where's yours? Because you've got 3 terms there, what you've done is you've squared each of those 3 terms, which is completely not the perfect square rule, right? You've got to be careful not to take, mathematicians are lazy, but they still think hard. Okay, so I'm all with the laziness, but you've got to think with it.
Is that right?
Yep. What approach are you going to take? Yeah, if you can see a pattern, think about applying it. I don't care if you get it wrong. The fact you're looking for it's good. Yeah, 2 perfect squares. 2 perfect squares, great. Hello, yep. There we go. Like I said, I might not have given you enough time to do it yourself, but that is the final line there, the final expansion there. X to the power of 4 plus 4x cubed plus 6x squared plus 4x plus 1. Now, there are 3 main ways that I saw there when I was walking around the room, and forgive me if I've missed out the one that I think no one did. Number 1, people saw, well, x plus 1 to the power of 4 is x plus 1 squared times x plus 1 squared. Tick, tick. That's good. That means you're looking for a pattern within a pattern. One person did it as x plus 1 squared, which is really clever. Okay, so they expanded x plus 1 first, x plus 1 squared first, and then squared that. The third way is that some people said, I think I can see a pattern here, but I'm not too sure what it is. I'm trying to figure it out. Love that. Maybe you got the pattern, maybe you didn't. That's okay. The fact that you're looking for it was really like big kudos, I think. The other way, which I don't think anyone did, and tell me if you did, No, is that you could have used the result from x plus 1 all cubed, which is down here, already worked out for you, and just multiplied that by x plus 1. Now, again, the reason why I'm pointing that out is not that that's the most efficient way of solving this problem, but in an exam, for example, often part B follows part A, right? So often you'll work out something in part A and you'll be told in part B something related to it. It might say hence use or hence solved. When you see the word hence, it means use the result from above that you just worked out. Okay, so a trick for young players is always see if a result you've just worked out is useful in the subsequent part. Okay, and with that in mind, let's see if you can beat me doing x plus 1 to the power of 5. Well, see if you can beat me, if you think you know what you're doing. Done.
Oh, Joe.
And why didn't I have to write out the triangle, Jamie?
Because you. Oh, it's X and Y. Yeah. It's X and Y.
Because I worked it out from that one.
No, because the values are just X and Y. So it's a multiple.
Oh yeah, there's that too. There's that too. It's pretty straightforward to get the bit. Look, this is the last slamming thing we can say. Even Sam got that. See how I managed to slam both of you at the same time with that? That was good. I'm quite happy with that one. Okay, I clearly worked it out. You can stop working, it's okay. I'm not going to make you do the whole thing. I clearly worked it out a lot faster because there's a pattern there. And if you were about the same speed as me, you've either come across a pattern before or you've worked it out. Yeah? So in terms of if you didn't see the pattern, you could have gone x plus 1 multiplied by x plus 1 to the power of 4. I didn't expect anyone to get the pattern, by the way. So you could have gone x plus 1 times by that, and that would have got you there. You could have gone x plus 1 all squared times x plus 1 all cubed and used those expansions. So there's a few things you could do to get there to shortcut your way through. But there's an even better shortcut. And what I'd like you to do, and I apologize if I'm going a bit slowly for some who already know the pattern as opposed to have guessed it. What I want you to do here is I want you to write out, I'm just going to go coefs for coefficients. Write the coefficients out. We've just done all these. So we're going to start off with x plus 1. I'll remind you what coefficient means in a second. X plus 1 all squared. X plus 1 cubed. X plus 1 to the power of 4. And x plus 1 to the power of 5. So coefficients means the number part of the term. Okay? If there's no coefficient visible, the coefficient is understood to be, yell it out. Yeah, because 1 times something is itself. So, for example, the coefficients of x plus 1 are 1, and then you can write the constant number at the end as well, 1 and 1. So do the same thing for x plus 1 squared, cubed. So you just need to read it from the problems you've just done. Just read it from the problems you've just done. I'll do the next one as well, just to make it clear. So it's 1x squared plus 2x plus 1. So it's 1, 2, 1. You got it, Sam. So you're just writing the coefficients down, the bits that aren't x, effectively. By the way, the last number, which has no x's in it at all, is called the constant term. So a variable is a stand-in for a number that might change depending on each time you apply the problem. So it's variable, it changes, whereas constant never changes. Okay, so any term that has no variables in it, it never changes, and so it's a constant. Hope that makes sense. Because you'll come across it. You'll come across things like, what is the constant term in this expression? You're just looking for the term that has no variables in it. Okay, I'll fill that in for you. Now, some people already know what the pattern is because you've been naming it. So you can hush. And all I'll say to you is, and even if you know the pattern, you might not say what I'm looking for anyway. So if you know what this pattern is, if you've seen it before, then just hush down for the time being. For those that have never seen this before, I just want to ask, can you see, just looking this way, don't look this way, look this way. For each of these here, is there anything that pops out to you as being a pattern? You know it, so put your hand down. Oh, thanks. Yeah, otherwise the pattern isn't great. Thanks, Sam. Again, nothing too obvious. Sorry, wrong way around. Nothing too tricky there. What can you see? Nothing at all sticks out? Thank you, Isabel. Begins and ends with a 1. Okay, every single time when we do this expansion, it begins and ends with a 1. Thank you. What else have we got? I can think of 2 other things we can see. Sam? You've been dobbed in.
Yeah, the number underneath is the product of the 2.
Sorry?
The number underneath is the product of the 2 top ones.
Thank you, the sum. But yeah, thank you. That is true. And I'll spell that out in a second. That's what you're saying is absolutely true. That's looking downward that way. But looking across ways, what else do we notice? You've got to be good at noticing things and naming them up because sometimes it leads you to uncover truths. Isabel? Yeah, symmetrical. Yep, same backwards and forwards. So in every single line here, if there's an odd number, there's a number in the middle, and it's the same up to that, and then it goes back again. And if it's even, it just goes up to a certain point and then goes back down again. It also ascends and descends. So it's symmetrical. Thank you. One last thing maybe you could observe. Something relating to what's happening on the left-hand side here and what's happening inside that sequence there. Yeah, or the power. Yep. Thank you. Okay, so that's true for each power. So if I said to you, I'll just have to go onto a new page for this. If I said to you x plus 1 to the power of 10, we know the first coefficient is going to be 1, the second coefficient is going to be 10, and so is the second last one, and so is the last one. So we've got that already. So that's a pretty good start. The other thing is, if you look at the count of the coefficients, we've got 1, 2, 3 terms here, 1, 2, 3, 4 terms here, 1, 2, 3, 4, 5 terms here, 1, 2, 3, 4, 5, 6 terms here. So how many terms are we going to have in this one? So 11 terms, thank you. Okay, so always 1 more than the power is what we've got there. So there's a whole bunch of things we can see, and we would anticipate if we were doing an expansion like that. Now, the last pattern is difficult to see unless, you're sort of guided a little bit more efficiently, I suppose, and I won't do that. But the last thing is that if I type those into a Word doc and then centered it, we would also see a pattern, and that's the one that Sam mentioned before. And that is, if I take x plus 1 all squared, the coefficients were 1 and 1. And then if I take, x plus 1, it'd be 1 and 1. Then x plus 1 all squared was 1, 2, 1. Then x plus 1 cubed was 1, 3, 3, 1. X plus 1 to the power of 4 was 1, 4, 6, 4, 1. And x plus 1 to the power of 5 was 1, 5, 10, 10, 5, 1. And what Sam pointed out before was that if you add the numbers up, you're getting the number underneath. Put arrows on them so it's a bit more obvious, I suppose. And yes, we'll put a name to it now, that this is called Pascal's triangle. Unfortunately, the triangle has a bit of a flat top to it, so I'll explain why in a second, but we can also put a 1 here. So the pattern for Pascal's triangle is start and end with a 1, and then the coefficients in between are just sums of the row above. Okay, so can you please write down into your summary book Pascal's triangle, and I want you to work out the coefficients for x plus 1 to the power of 6. So you might want to put the x plus 1 on the left-hand side. Because I don't have lined paper here, it might be hard to see, but that's x plus 1. That's x plus 1 all squared. So I want you to do x plus 1 to the power of 6 as well. So I'll give you 45 seconds to do that. Get it into your summary book. Go as far as x plus 1 to the power of 6, just so that you've got practice in doing a line you haven't seen before.
Richard?
Yeah.
That's all good. I just lost you a little bit on that one of the starter questions. I kind of daydreamed off and didn't find a second.
Yeah, sure. So I'll just go through it again. So if we have a look at this one here, what I'm going to do is I'm going to take out a fact. I'm going to look at this bit here and take out a common factor of -1. 1 multiplied by what? So -1 times b will give me minus b.
Yep.
-1 times what will give me positive c?
-1.
-1 times what will give me positive c?
Oh, minus c.
Good. So by taking out a common factor of -1, and we just don't tend to write the 1 in, by taking out a common factor of -1, we effectively change the sign of each of the things inside the bracket. So b plus c becomes b minus c.
Right.
Okay. And the reason why we do it, that should have been a minus there,
Yeah.
is that we've now got a plus b minus c, a minus b minus c. Yeah. Does that make sense?
Yeah. Cheers.
Okay, so it's a really powerful way, well, a really good shorthand way of being able to expand a fairly it's not straightforward, but a fairly simple looking expansion there. So just to make sure you got it right, I'll just do it in a different color so you can see it. Start with a 1, then add them up. 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6, and then put a 1 at the end. So we've got our coefficients. Now I call these starting coefficients. Starting coefficients. Because sometimes the final line does not have those numbers in them, because all of these expansions are just 1x plus 1. If I made it 2x plus 1, or if I made it x plus 2, that's going to change the whole flavour of it. But it gives us a starting point. The next thing I want you to have a look at, maybe let's just concentrate on x plus 1 to the power of 4. Can you see, well, have a look at the powers of x there. What's happening? They're decreasing one at a time. So it starts off with the full power of x to the power of 4, and then the next one is x to the power of 3, And then the next one is x to the power of 2. And then the next one, there's no power, but we know that's just x to the power of 1, right? And even the last one has a power of x. What's the power of x on the last one? Yeah, because anything to the power of 0 is just 1, right? So artificially, we can put an x to the power of 0 there. So what that means is that the powers go down 4, 3, 2, 1, 0. Oh, and by the way, if I gave you this problem, I'll just go to a different screen just for my scribble pad. If I gave you this problem here, how would you expand that? It'd just be 1 for the same reason. Anything to the power of 0 is just 1. And that's why, oops, went to the erase button there. That's why the top of the Pascal's triangle works, because that top of the Pascal's triangle is x plus 1 to the power of 0, which has a single 1 as the result. So that's just a by the by. Okay, so the powers of x go down. Now, what I won't do, because it's just a little bit tedious, is if I got you to expand this, what you would find with that expansion is that you would get this. First of all, I've got my starting coefficients, right? So I've got 1, 4, that's a bit too spaced out. 1, 4, 6, 4, 1. Still not very well spaced out. Okay. So 1, 4, 6, 4, 1. I would then put my powers of x descending. So I would go x to the power of 4, x to the power of 3, x to the power of 2, x to the power of 1, and nothing. But here's the thing you haven't seen, and again, you can prove it for yourself if you want to. The second term goes up in powers. And so I'll do that in green, I'll do it in black. So that would go y to the power of 0, sorry, which we don't write in. So y to the power of 0, y to the power of 1, which we don't write in, y squared, y cubed, y to the power of 4. And then we're going to have pluses in between. And the second term determines that. So I'll just write that so it's decolourified there. So again, we'd have x to the power of 4, the 1's understood to be there, plus 4x cubed y, plus 6x squared y squared, plus 4x y cubed, plus y to the power of 4. And that would be the expansion of x plus y to the power of 4. Any questions about that? Is that making sense? So the first term goes down in powers, the second term goes up in powers. And if you can do that, you can pretty much expand almost anything I throw at you, really, as long as you draw a big enough Pascal's triangle. There's something else to notice as well. If you have a look at each term, so x to the power of 4, and then look at 4x cubed y, and then look at 6x squared y squared, and then look at the other two as well, what do you notice about the powers? Does anything stand out to you? Just looking at the powers themselves, ignore the variables so much, but look at the powers. Jamie, what did you notice? Four, 3, 2, 1, 0 and 4, 3, 2, 1, 0. So that's symmetrical properties there again, isn't it? So it's symmetrical. And that kind of makes sense really, because x plus y to the power of 4 would therefore be the same as y plus x to the power of 4. So thank you. There's one other thing I wanted you to say. Look at each term. Don't look at the sequence of terms. Look at each term by itself. Yeah, thanks again. The powers add up to 4. Can you see that? So that's just got a single power of 4. This one here is x cubed and y to the power of 1, right? We don't write the 1 in, but it's there. 3 plus 1 is 4. 2 plus 2 is 4. That 1's not there, but it is. So it's 1 plus 3 is 4, and then we've got a 4. So every single time, the powers add up to 4, and that's really a really important check for you. If the powers don't add up to 4 in this kind of expansion, then there's something wrong. Okay, let me just give you a problem to try now. You've got your Pascal's triangle. I'm going to stick to the power of 4 because it's big but not too big. And I want you to see what happens if we now do x plus 2. to the power of 4. Do that one. Callum, you all right? Is this something we just need to take outside? Is this Biffo?
Yeah, but she's on 5 minutes.
I'm putting money on you.
So I'm putting money on him.
You're putting money as well. Follow the pattern, but then simplify, right? That's the trick. Follow the pattern, then simplify. Great. Good. So x is going to go to the power of?
4.
Yep. Excellent. So look at your line. The next coefficient is 4. So you have a 4. So put plus 4. I'm just going to take you through this little bit. That's all. Plus 4 times.
What, which bit?
So rub that bit out, because we're going to be really systematic with the way we do this. Okay, so I go plus 4, and then put in brackets x, and we're going to go down a power, aren't we? So x cubed, isn't it?
Yeah.
Is that okay?
Yeah.
And then put next to it 2, or put in, I usually put brackets around them. So bracket 2, close bracket. So we've got 4 times x cubed times 2, okay, plus. Next coefficient is?
6.
Good. And then in brackets, what's x going to be?
Squared.
Perfect. And then in brackets, it's going to be
2.
2 what?
2
2 to the power of 0, 2 to the power of 1.
to the power of 2.
Great. Finish the line? Cool. Yeah, it depends on what you're going to do next. Keep going.
Times 2 to the power of 2.
Great. Yep. Now look. 2 to the power of 0, 2 to the power of 1, 2 to the power of, not a plus, but a
2.
times. So it's 6x squared 2 squared.
Yeah.
And then it's 4x2 cubed, and so on. What'd you call me?
I call Samuel silly boy.
Oh, that's all right then. That's like saying water's wet, isn't it?
He's got roasted salmon.
Looks good. I haven't done it myself, but I think it's. There's an X missing there, apart from that.
Oh, yeah. Oh, sorry.
16. 16 is my favourite number because 2 to the power of 4 is the same as 4 to the power of 2. Looks good to me. I haven't actually worked it out myself, but looks good to me. Where to start? Yeah. So let's just start. So you've got the coefficients there. You'll probably need a little bit more room than that. So let's do it underneath. So you've got your 1, and then you've got your x. So yeah, just do it in sequence. X to the power of 4. Yep. And now we do the next one. So plus 4. Plus 4.
Oh, here.
Just put your plus there. Yep, 4. And then we're going to go down 1 power of x. Yep. And then up 1 power of 2. So that's times by 2.
What's the up by 2 thing?
So just times it by 2, and I'll explain. You've got 2 to the power of 0, 2 to the power of 1. So now write plus 6. Go down 1 power, x squared, up 1 power.
Have to add 2? Was that the thing?
The powers will, yeah. So times by 2 squared.
Oh, because they got to get to there.
Yeah, excellent. So 2 to the power of 0, 2 to the power of 1,
X
2 to the power of 2,
plus
times
2 to the 4.
2 cubed.
Oh, plus the 1, yeah.
Yeah, follow the number 1, 2, 3, 2 to the power of 3. Perfect.
It gets to the 4
And then you're up to the 4. Yep.
plus.
Follow the powers. 2 to the power of 1, 2 to the power of 2, 2 to the power of 3.
2, so 64.
We'll just put 2 to the power of 4 and just start there. 2 to the power of 4 is 16.
Oh, yeah.
2 2s are 4 2s are 8 2s are 16.
Just one
X to the power of 4, 8 x
simplifying this, do I go
squared.
8x cubed?
Yep. Okay, just conscious of time, I'm going to just finish that off. Most of you got there, I think. Sorry, normally I'd put a couple of extra problems down for people who have finished just to give yourself consolidation. But yeah, I'll show you how I've set it out as well, because you might want to do the same, but you don't have to. I always start, so if I was in an exam, probably one of the first things I'd do is I'd probably stick Pascal's triangle down somewhere. Until I got to the line that I wanted. So that's just so I know it. And then what I would do is I'd explicitly write down the coefficient, even though one's a bit useless. And then I tend to put each of the terms in brackets just for my first line. So I'll go x to the power of 4. And then I'll go plus 4. So I'm just picking the next coefficient, 4. And then I take the first term and go down a power and then take the second term. And then I keep on going. So 6 x squared 2 squared. I'm not trying to do too much at once because I find it a bit confusing. Plus 4x 2 cubed plus 1 times 2 to the power of 4. So my first term is going down in powers, 4, 3, 2, 1, 0. When people pack up when I'm trying to finish off a lesson, it puts me off and I find it disrespectful because it's like saying, hurry up, I want to go. I don't like it. It makes me feel uncomfortable, and I think you're sending me a signal you don't want to. Is it the last time I have to say that? Pack up when I ask you to, please. 2 to the power of 0, 2 to the power of 1, 2 squared, 2 cubed, 2 to the power of 4. The last line then is just simplifying it all together. So 1 times x to the power of 4 is x to the power of 4. I can multiply the numbers together here. So 4 times 2 is 8. So I've got 8x cubed. The next one, I'm just going to be doing it in my head. 2 squared is 4 times 6 is 24. Next one is 4 times 2 cubed. 2 cubed is 8. 8 fours are 32. And then 2 to the power of 4 is 16. So that's my full expansion there. Homework, really simple homework for Monday. There's a trick to it, so think carefully. Your homework is to use Pascal's triangle to expand that. X minus 2 to the power of 4. Do you want me to put that on Google Classroom as a reminder as well? Yep. That's it. Thanks, everyone. Have a great weekend. This video will be available to you sometime this morning.